had it here, and we had it in varying positions, and we measured the activity of the leg as part of the experiment. But we had to measure the open lab because we don't have a whole body on it. And so I told Rajiv, we better get a background. And I have, fortunately, a very good colleague up in our cadaver lab who, this was towards the end of the last spring semester, who was willing to cooperate. So we set Rajiv up, and it turns out our dental hygienist students only deal with the face and the head of the cadavers, and so they had a lot of cadavers with intact legs. So the first thing is, Rajiv walks in, and the guy says, well, what leg do you want? And I don't know. And, okay, we'll take this one. And he pulls out a knife and hacks off the leg. What he didn't know was Rajiv walked up to the bio lab, and so he handed Rajiv the leg. Rajiv put over his shoulder, walked right to the So it was a very interesting situation. But, we're cowboys here. We'll just get the job done. So Rajiv is officially a cowboy.
How long did it take you to get him out of jail?
I think they looked and they said, that can't be that.
The topics of my presentation is about a new leg voxel model in two different positions for simulation of non-uniform distribution and the leg bones. I know it's talking about quantum conductor grammar, it's not a good idea. I'll go contradiction, goal of the study, materials, methods, results, and discussion and conclusion. So, on long-term basis, transuranics are typically classified as bone-seeking elements. To assess the activity of transuranics, like Symposium 241, deposited in the skeleton, in vivo measurement must be carried out in the region of the body having high bone content and low surrounding tissue, like the skull and the knee. Various kinds of counting systems have been developed for in vivo measurement. These counting systems need an appropriate calibration method, and the calibrations routinely performed by measurements of phantom. Two types of phantoms usually used for efficiency calibration: physical phantom and computational phantom. Physical phantom capable of representing human body have been used for efficiency calibration since 1950, and the classical method applied for efficiency calibration is performed with physical phantom that are loaded with non-radioactive materials in the region of interest to relate measured count to radionuclide body burden for a given geometry. Computational phantom divided into stylized phantom and voxel phantom. The first revised stylized phantom in the history of computational model was developed by Fisher and Snyder at Oak Ridge National Lab in 1966. Stylized phantom described the shapes of human body, including internal organs, by mathematical equations describing the cylindrical, spherical, or cortical surfaces. Voxel phantom, a mode from tomographic medical image, like MRI or CT scan. The organs and tissues are manually or semi-automatically segmented from the image, and the segmented two-dimensional pixel data are stuck into three-dimensional voxel matrix. Resulting matrix are close to the original medical image, higher elastically describe the human anatomy. Since 1985, when the first voxel model was introduced by Gaps and others, a representation of a head and trunk was built from CT image of a female cadaver and was used to calculate the effective dose from radiography. Since that date, many researchers have developed and used voxel phantom and Monte Carlo simulation to calibrate in vivo monitoring system to evaluate the amount of Symposium 241 deposited in the skeleton. Most of the leg and knee voxel phantom that have developed and used for this purpose was considered only when counting geometry, which is straight leg position. The leg voxel model were created based on CT image of the physical phantom and segmentation of three materials: air, bone, substitute, and and tissue substitute. The uniform distribution of radioactive materials was only the choice in the physical quantum. However, the radioactive materials in the human leg bone are non-uniformly distributed. So to answer these questions and to assess the amount of activity deposited in the skeleton, to assess the amount of activity deposited in the knee, and then related to the entire activity in the skeleton, a suitable position of the leg by which all the knee bones contribute to detectable activity should be found. So based on the analysis of anatomy and construction of compressed bone in a knee, it intuitively appears that bent leg position allow maximum of knee bone surface area to be exposed to the detector, use the detector rather than with a straight, and allow maximum activity to be measured rather than allowed with a straight leg position. So the goal of this study is to construct a new high-quality leg function model that contain most of the main tissues and organs of human leg. Voxel model is used with an MCNBX Monte Carlo code to simulate different leg position and non-uniform distribution of radioactive materials throughout the leg bones. This phantom to be used for efficiency calibration of in vivo monitoring systems. In the materials on method to develop the voxel phantom, we use case of americium contamination. The gentleman was presented by United States Transuranium and Uranium Industries, USUR case 846, was a glove box operator who prepared an estimated 50 breast gold foils. Each contained 200 milligrams of americium oxide powder. Between 1964 and 1967, this person was repeatedly internally contaminated, most probably by americium oxide via chronic inhalation. He died about 40 years post-exposure from pancreatic adenocarcinoma. So the USUR case 846 was scanned into a different position, straight and bent. After that, it was sent back to USUR for radiochemical analysis. Image constructions was performed with a grade 5, 12 times 512, pixel wide 0.781 and 0.976 millimeter for a straight and bent leg respectively. The slice thickness of the image was set at 2 millimeters. All CT image was saved in DICOM format. And the DICOM image were subsequently imported into 3D Doctor, 3D modeling and image processing software for CT scan data. And these slides show one image of CT scan and the image profile of the leg, and the image here is ready to segment. And segmentation may be performed manually or semi-automatically on CT image of a real leg, or on CT image of a real human body, or CT image of physical phantom. Manual segmentation of CT image of real leg could be challenging and require long processing time due to tissue variety and layers of real leg. However, in this study, manual segmentation was considered to be necessary because the bone was the most important part in the phantom. So a total 36 individual objects were segmented manually, considering each pixel of CT image according to the image resolution and ICRB 110 recommendation about voxel phantom. The organs of interest were divided for the tissues into skin, adipose tissue, muscle tissue, blood vessels, lymphatic node, and bone cartilage. For the bone, were divided into cortical bone, clavicular bone, and medullary cavity. To account for non-uniform distribution of radioactive materials in the leg bone, the bone was divided into 30 small parts, and these parts was according to dissected bone section. And I keep saying non-uniform distribution of americium because according to radiochemical analysis for this case and all the cases that's published on the USTR website, it was found that the concentration of americium in different parts of the leg, in distribution should be the concentration is equal in each part or each piece. So we consider, or we say that uniform distribution. So during the segmentation, the bond was sectioned according to dissected bonds part prepared for radiochemical analysis into 30 sections. And this, the weight of the segmented section in the voxel phantom corresponding to the weight of each piece of the bonds that was obtained from radiochemical analysis. And that's the total weight of the bond in the phantom and corresponding to total weight. And here we see that's 0.1 and 0.13. It's not that sensitive, but it's the summation of the weight of all the pieces. So we just put the summation of one value. So during segmentation, the segmented image were saved as project file. Once the segmentation is finished, the project file was exported to a boundary file and saved. And this shows one slice of segmented image on the border of each organs, bone, tissue, and the skin. And this is the one slice of the boundary file. The boundary file is ready for segmentation, it's ready for voxelization. And the software voxel lattice editor is originally used to manage voxel model and convert voxel file into format used in NCNPX input file. This software was developed by National Internal Radiation Assessment Section Human Monitoring Lab in Canada, which Dr. Kramer will cover in detail. The voxelizer was used in this study to convert the boundary file into voxel file and saved. The voxel file was then converted by the software to repeated structures to describe the geometry of the light voxel model. The result of this study, a new light model with 36 objects plus the air object that surrounding the phantom was developed. The phantom was created based on manual segmentation of CT image of human cadaver leg. The phantom could be used to more accurately model non-uniform distribution of radioactive materials in the bone. And the weight of the bone in the voxel phantom is identical to that in USUR 846 leg. And this image shows the voxel phantom, the entire region of interest, the left, the middle, the outer shell of the bone, the cortical bone, and on the right, the trabecular bone and medullary cavity. The phantom was modeled into different positions, straight and leg. The bent position appears to be first developed leg voxel phantom based on CT scan of a real leg. And the phantom straight leg position consists of 592 or 23 voxels, and bent leg position consists of 377, 567 voxels, and the weight of each piece in this voxel phantom is identical to the real piece that analyzed. And this figure shows the final result of the voxel model inside an air box, and it's ready to use MCNPX input file to simulate any measurement and calibrate any in vivo monitoring system. In conclusion of this study, a new leg voxel model in two different positions was pulled based on CT scan of USUR case 846 leg and detailed from radiochemical analysis of small bone sections from the same leg. This voxel model representation of a human leg could be provide a substantial enhancement in Monte Carlo simulation because its model more accurately model non-uniform distribution of radioactive materials throughout the leg bone in a state of assuming uniform distribution. And this was accomplished by radiochemical analysis on the leg from USUR case 846. The phantom contains most of the main tissue and organ of a human leg and consists of suitable number of voxels with good voxel resolution. The voxel resolution and number could be improved for any other application or studies. And that's the end of
Any questions for the think another successful John Horan Symposium.